All right. So, topic here. First topic we got here is a resonance structure, and so pretty easy way to describe this is just to look at these three structures down here and take a look at the only thing that is different. So, kind of look at those. What is the only thing that's different? Well, hopefully, you're able to spot the fact that the double bond is either on the top, on the left, or on the right. So really the only thing that's different in these three structures is where you put the double bond. So what happens in a structure is it's not quite as easy as just, hey, I'm going to draw it on a piece of paper. This is what it looks like. In reality, in real life, this is just a model that we're trying to kind of, show something that actually exists in real life. But what this is actually a combination of all three. So resonance structure is when we can draw a structure multiple ways. And so that's kind of what's going on there is that we have this structure, and you can see that I just drew it three different ways, and they're all correct. So resonance structure is going to be, we got three lines here. That's going to be multiple possible correct structures. So multiple possible correct structures. And so a lot of times when you draw something, you can put a double bond here or there, or a triple bond here or there. And in the end, you might be creating different versions of the same thing. So why do these slightly different structures exist? We're going to start talking about this quite a bit. This idea of delocalized electrons. So what that means is that the electrons get to move around, right? So they get to move around. So electrons are not like tied to this oxygen or this oxygen. The idea of delocalized means that the structure has a pool of electrons. So it has like a set of electrons, and those electrons kind of move and flow within the structure, which is why the double bond in all reality is actually moving. And so it's maybe here, and then maybe here, and then maybe here, and it's kind of switching around. So that's a little more complicated than you need. But this idea of delocalized electrons is really, really, really important. And it just means that the electrons are not attached anywhere. They are free to move around. So you might want to write that down. That delocalized means that those electrons are free to move. And so maybe I'll just put this here. Electrons are able to move, or maybe we want to put are not attached to any specific atom. So basically the electrons are not attached. They are able to move, and that's kind of the idea. All right, formal charge. So what the heck happens if you do have multiple ways to draw a structure, and they are a little bit different, right? Like, so you could put maybe a double bond in, or a triple bond, or you have different options. If you have options, one of the options should be better than the other options. And the way to figure it out is this concept of formal charge. Now, this is going to be on the test. Like, this is on the test. And every year, students miss this because they don't go back and look at formal charge. But you want to write down that this is going to be a test question, and you need to solve it using formal charge. Okay, so it's a test question, and you need to use formal charge to solve it. So the test question will say, okay, you got these structures. Which one's the best? The way to figure it out is through formal charge. And so how do you figure out formal charge? So the first thing is that you have to apply a concept of formal charge to each of the atoms. And so each atom gets a number, right? It gets a formal charge. Now, this is not a real number. This is a number that helps us determine if you have the best structure. So how do you do it? Well, the first thing you do is you're going to take the valence electrons, so whatever your valence electrons are for that particular atom, and then you're going to subtract half of the bonds or half of the bonding electrons and then all of the lone pairs. All right, so we're going to take valence minus half of the bonding electrons and the lone pairs. And so I think it's probably easier to write it like this. And I'm going to rewrite it down here, that formal charge. This is the easiest way to remember it. So formal charge equals the valence number minus the bonds and then minus the dots. So we're going to take our valence number and we're going to subtract all of the bonds and all of the dots. Okay, so let's just do a quick one up here. Let's do like assign a quick one so you can kind of get the idea. So we'll just take an example. So let's look right here. Let's look at this particular oxygen right here. Let's look at this oxygen right here. Oh, didn't circle the oxygen. Try it again. Let's look at this oxygen. Okay, so we're going to do this. So oxygen's valence is 6. I'm going to subtract the bonds. There's 2 bonds because it's a double. Minus 2. So minus 2. And then minus the dots, which there's 4 dots. And that equals 0. So the formal charge for that particular oxygen right here, we would say that it has a formal charge of 0. And you would do that same thing with this oxygen, and the nitrogen. So everything gets a number. Now, let's look at these rules. When you add up all of those numbers, the sum of all of the formal charges needs to be 0, or if you have something with a charge, so like polyatomic ions have a charge, so like NH4 plus 1, there's ammonium. When you add up the formal charge to this one, it would equal plus 1. Normally it's 0 because most things don't have a charge. Okay, adjacent atoms should have formal charges with opposite signs. That doesn't always work out, so I wouldn't worry a ton about that. And then here we go. This is the really important one. This is what's going to get you the answer. The best structure has no formal charges, meaning that all of the values add up to 0, right? So like this is how you're going to figure it out on the test. This is what you want to remember right here. All your formal charges should be 0. The best structure is going to have 0. So that's how we're going to figure it out, is right here. That's what we want to remember. Now, the formal charges should be small. So like you shouldn't have like formal charges like 6 and 8 and 9. They should be small. And then if you have a tie, the most electronegative atom should have a negative formal charge. So like if I had a tie and I was comparing like oxygen versus nitrogen, oxygen's more electronegative, so it should be the one with the negative formal charge, okay? Don't worry about ties. I will not give you a tie on the test. You just need to find the one with the zeros. So, all right, let's do a problem. Or look at a problem, and then we'll do a problem. Okay, let's zoom in here. So this is a weird one. You're going to see right away that this is a weird structure. This SO2 is an odd structure because it has these two options. And so one option looks like this. So this is one of the options. Okay, so that is this one, number one. Okay, and then number two looks like this, which is like super squirrely, but there are chemicals that we're going to find out that can do this, where they actually have more than 4 attachments. And so that's the thing that we didn't teach you last year because you didn't need to know it, but there is a little bit of squirreliness that can happen. So these are the two possible structures. So this is number 2. So if we assign formal charges, we can figure out what the best one is. So let me do the formal charges for the one in blue. So the oxygen, this oxygen would be 6, that's the valence, minus 2, that's the number of bonds, minus 4, that's the number of dots, that equals 0. Okay, the sulfur is also has a valence of 6. So sulfur would be 6. So I'm doing this now. 6 minus 3 bonds minus 2 dots. So sulfur would be 6 minus 3 minus 2. So 6 minus 5 basically is plus 1. And then this oxygen would be 6 minus 1 bond and then minus 6 dots. And that's going to equal -1. Okay. That's not super great because you have the numbers 0 for that, plus 1 for that, and minus 1 for that. Because remember, I told you the best situation would be if we could get all zeros. So now let's draw a line there and let's switch the pen to green and let's do this one. So this oxygen, 6 minus 2 bonds minus 4 dots, that's 0. Sulfur, 6 minus 4 bonds minus 2 dots equals 0. And then this oxygen is 6 minus 2 bonds minus 4 dots, which is 0. So this one is actually the best one because it's a 0. Let's go to blue. This one's a 0. This one's a 0. And this one's a 0. So like that is the winner. So because everything is a 0, this is actually the winner. This is the best structure. And the weird thing is that it looks weird because this sulfur in the middle actually has 2, 4, 6, 8, 10 electrons, which is super weird. And we told you last year you could never do that. But there are exceptions now where that is going to be acceptable. So you're going to start to see things like that. So that's the structure you'd pick. Even though it looks weird and looks like it shouldn't work, it does work. And so we conclude that that's the best structure because you can see the answer right here in the notes. 0 plus 1 minus 1 versus 0, 0, and 0. So the key is get all the zeros and then that formal charge will work out. So okay, so here's an example. I want you guys to try to work through this one. So kind of pause the